In this video, we're looking at the vector cross product. So it's another way to sort of multiply two vectors together. In this case, you get a vector out rather than a number like what we did with the dot product. So first of all, we need to revise determinants of matrices. So a determinant usually looks like det of a matrix A, or sometimes A with bars around it, or even the matrix with bars around it. But at any rate, what this is you do 1 times 4, take, and then the other diagonals, 3 times 2. So you get 4, take 6, so there's minus 2 there. And that's something called the determinant. Basically what the determinant does is it tells you whether or not the matrix has an inverse. Now, if you do a 3 by 3 matrix, there's still a process of finding the determinant. Basically what you do is you take that with that. Now it's going to look a little bit weird, but det B, it's going to be 3 times the individual determinant. So just like that. And then you go each pair. So pretty much when you pick 3, you cross out those two. So the next number we're going to pick is 2. And then we're going to get this determinant here because we're sort of crossing out the numbers under 2. So you've got 2 with the other determinant, 0, 5, 2, 1. And then we do the same process with the 4. So you pick the 4 and then you do the other determinant here. So that's 4 with 0, minus 1, 2, 3. Now, the way that it goes is plus, minus, plus. And if you're doing a bigger matrix, it would keep alternating like that. But the key thing is the middle term has a minus sign. Make sure you don't forget that. It's very easy to miss. Now we just need to work out each determinant. So this is 3 lots of minus 1 times 1, take 5 times 3. Then this is minus 2. It's 0 times 1, take 5 times 2. And then plus 4. It's 0 times 3, take minus 1 times 2. Just like that. Okay, so now that we've got all that, we can work out what these determinants actually are. This is 3 lots of minus 16. Take 2 lots of minus 10, plus 4 lots of 2. And we can pretty much just chuck that in a calculator and then evaluate it. All right, so get all that typed in, and then the determinant is just minus 20. Okay, you might be wondering, why the heck are we doing matrix determinants? It's the vectors topic. And the reason is when we calculate the cross product, we actually calculate it through doing a determinant. It's a little bit weird. But we want to cross product these two vectors. So what this equals is this. It's a big determinant. It's a 3 by 3 matrix. You put the two vectors that you want to cross in like that. And the top row is the vectors I, j, and k. A little bit weird, but that's sort of how it works. Now, just as a little reminder, I is a vector which sort of goes along the x-axis, j is a vector which goes along the y-axis, and k is a vector which goes along the z-axis. So those are your sort of like univector-y things. Now we can just work this out. So with this cross product here, it's going to be I lots of the first determinant, 3, 2, 0, 5. Then our next bit is j. With the other determinant, 1, 2, 4, 5. So remember the method for that was sort of picking j and then picking the two that aren't underneath j. Then it's k times the other thing. So it's k times 1, 3, 4, 0. Remember it goes plus, minus, plus as well. That minus sign is very easy to forget when you're doing the cross product. So this is I lots of, let's go 15, take nothing. And then it's j lots of 5, take 8. So 1 times 5 and 2 times 4. Yeah. And then it's k lots of 1 times 0, take 3 times 4. So this is 15i. Take 3, well, it becomes plus 3j because the two negatives will cancel out, minus 3 and minus in front of the j. And then it's take 12k. So if we write this back as a vector, that's going to be 15, 3, and minus 12. Just like that. So that is what you get when you cross these two vectors together. All right, so we need to interpret the cross product geometrically. I've got those points A and B as being sort of like those original two vectors, so to speak. But generally, when we talk about them as vectors, we're thinking about lines coming out from the origin. So I've got those two black lines representing those vectors, those original two that we started with. Okay, point C down there is sort of the result that we got from the cross product, and let's draw a line straight out to it. Basically, what the cross product does is it finds a vector which is at right angles to both of your original vectors. So if we look at sort of this dashed line going out to C, and we look at the angle that makes with A, if I can sort of get the camera to point at it correctly, the angle between that black line going through A and then the dashed line going through the result from our cross product is 90 degrees. And same if I get it at the right angle correctly with B and that line out to C also makes 90 degrees. So what the cross product does is it finds a vector which is at right angles to the two original vectors. And just for example, if I wanted to check that this is true, I could do 1, 3, 2, and I could dot it with 15, 3, minus 12. If you work that out, you're going to get 15 plus 9 take 24, which is 0. So yep, we have these two vectors are at right angles to each other. And if you want 405 dotted with 15, 3, minus 12, should give you 4 times 15, so that's 60, plus nothing take 60. So yes, that's 0. So those two vectors are at right angles as well. I'll mention the original vectors were not at right angles to each other. It's just that this third vector we got here from the result is perpendicular to that one, and it's also perpendicular to that one. Now, next cross product we're going to do is I times j. So to be really clear what we mean here, this is the vector 1, 0, 0, and we are crossing it with the vector 0, 1, 0. Now, essentially what this looks like is we've got our x-axis, y-axis, and z-axis here. This vector along here is I, and this vector along here is j. Now, if I want a vector which is perpendicular to both of those, it's probably going to be this one up here, k. So I'm hoping that I actually get 0, 0, and 1 out of the cross product, and we'll see whether we do or not. Okay, so to do the cross product here, I cross with, well, I'll write it as this original vector here because we're going to use i's and j's in the cross product, and that might get a little bit confusing. But we're starting with 1, 0, 0. That's the first vector we got in our cross product, and 0, 1, 0. And now we'll just work through this process of finding the cross product. So the first step is I times this determinant here. So it is going to be 0, 0, 1, 0. Take j, don't forget the minus sign, and it's times sort of these two rows here, or these two columns, 1, 0, 0, 0, plus k times the remaining two that aren't under k, 1, 0, 0, 1. So this gives you I lots of 0 take 0, take j lots of 0 take 0, plus k lots of, that's 1 times 1, take 0. What you're left with is essentially the vector k, which is 0, 0, 1, as we would expect. So yeah, it does find the vector perpendicular to both. I just want to warn you a little bit though. Let's calculate j times I, so let's do the cross product the other way around. So this is ijk. Last time I had this x vector, well, like 1, 0, 0 was on the top and 0, 1, 0 was on the bottom. I'm actually just going to swap the order now. We'll see what happens. Okay, so if we work this out, we're going to get I lots of this determinant, take j lots of this determinant, plus k lots of this determinant. Now it works out almost exactly the same, but this last bit, it's 0 take 1. So we're actually going to get minus k for this answer, which is 0, 0, minus 1. Ooh. So we do get different answers. Now, minus k is a vector which points down like that. And I'm hoping you can agree that this is still at right angles to your two original vectors. In fact, there's infinitely many vectors that could be at right angles. So for example, just like a longer vector up here would also satisfy being at right angles to both. So the cross product, it does actually matter what order you do it in. So in general, V cross with W does not equal W cross with V. We have to be very careful. And it's probably our first example that we've had seriously where the order actually matters when you're timesing things together. So be very, very careful with this.